So we come to one of the most confusing, misinterpreted, complicated things in physics so far. It's a good thing we don't have to know everything about it because it is very complex, and that is special relativity. So special relativity, a quote from Brian Greene, who's a preeminent scientist of the day, is involved with string theory. He says, no matter how hard you try to teach your cat general relativity, you are going to fail. Special relativity is very, very complex. It does not quite match with what you would expect in the world. You do need to know how to do some of these things and understand that there are real applications that your life depend on. So it says, number one, students should understand the difference between normal relative velocity and light relative velocity, and that students should understand the effect relativity has on time and length. And finally, students should understand the experimental evidence supporting the theory of special relativity, and that's a key one. You should also be able to show applications of the theory of special relativity. So first, the relative velocity. When two cars drive towards each other, their velocities add together. That's why whenever you have a head-on collision, it is always much, much worse than when you have a rear-end collision, because when you have a rear-end collision, if somebody's going 60 miles an hour, the other person's going 55, it's like a 5-mile-per-hour collision. But if you have two cars that are headed towards each other at 60 and 55, it's like a 115-mile-an-hour collision. So it's very important that you understand that. We talked about that in terms of adding cars together. This question says two cars move towards each other at 65 miles per hour and they collide. What is the velocity relative to each other? So we talked about this earlier in the year. Just as a review, you have one car moving this way, you have the other car moving this way. If they are both moving at 65 miles per hour towards each other, the collision that would result would seem like they were going 130 miles per hour because you would add the two together. Now, if they were going in the same direction, they could actually never collide. They can get as close as possible, but if they have the same velocities, the resulting velocity between them would be zero. So they could never actually collide. Light. So light is the fastest thing in the universe. But if you were to take a look at this and say, if you have two flashlights that are moving, that are opposite of one another, you would think that the light travels towards each other at 2c, which is the speed of light, because one light particle or wave would be traveling at the speed of light, and the other light wave or particle would be traveling at the speed of light. So it's like they're traveling at each other at 2 times the speed of light. But light is the fastest thing in the universe. So you can't have two particles of light or two pieces of light traveling at each other and then go faster than what the fastest thing in the universe is. So the question is what results? This is Einstein's special relativity. It was basically two postulates. And it says this: the laws of physics are the same in all inertial reference frames, and that the speed of light in a vacuum is equal to the value c independent of the motion of the source or the observer. So if we go back to our flashlights, no matter where I am, I should see this flashlight's light moving at the speed of light, and I should see this one moving at the speed of light, no matter if I'm traveling with this light beam or I'm traveling with this light beam. So this sets up an interesting problem in that, okay, if you have two light beams, then what happens as a result of that? If nothing can travel faster than the speed of light, what happens if I walk towards this flashlight? The light would, you would think, approach me at the speed of light plus whatever I'm walking at, but it turns out that's not the case. Instead, what you would see is you see a paradox that develops, because you can't go faster than the speed of light. So what instead happens is you have two choices, with the first one being called time dilation. So time dilation is one resolution in the fact that time slows down as you approach the speed of light. So remember, we have two things that are involved in the speed of light: distance and time. So if we have time dilation, where this term actually increases, well, increasing the time has an overall effect of decreasing the supposed difference in the speed of light. So that's one resolution, and it has been used by many science fiction writers to say, okay, well, we'll just shoot people around at rockets at close to the speed of light, and they will age much slower, and they'll be able to come back, and everybody that they know will be gone, but they'll still be very young. There is some question about that, but there is experimental evidence to support this time dilation factor. And the number one is the GPS system. So the GPS system is very common. It's available on most phones and in cars and so forth. But what it does is it actually uses triangulation. There's multiple satellites that send a signal to your GPS receiver. And the interaction or the cross-reference of those GPS satellites can tell you where you are. But the key thing is that the clocks must be in sync. The clock in your GPS and the clock in the satellite has to be in sync. But because the satellites are moving so fast to maintain their orbit, their clocks actually run slightly slower. So you have to use corrections to say, okay, 5:04 on the satellite, maybe 5:05 on the Earth. And it's not quite that dramatic, but those corrections are necessary to occur to put you in any sort of right place. If you don't have that correction, you'll be off by more and more and more every time since you first fire up your GPS. So the formula for this is this. You have TV, which is the time dilation factor, or the new time, is the original time, and then you have this term right here. Sometimes this is called a gamma term. It's just the square root of 1 minus v squared over c squared. Now, if you notice, people say, well, shouldn't this be the case in all relative velocity additions? And it is. But when you start to look at very small velocities, like 10 meters per second, if you get 10 squared divided by the speed of light squared, and then you do 1 minus that and take the square root, you get basically 1. So there really is no time difference. The only time you start to see a time difference is when you actually approach the speed of light. As you get closer and closer and closer to the speed of light, like let's say, for example, this is the speed of light, and this is 0.9 of the speed of light. Well, 0.9 squared would be 0.81, and then the c's would cancel, and you can actually get a pretty big factor here, making this time and this time very, very different. But they're only different as you approach the speed of light. Okay, so in this question it says twin A stays on a rocket while twin B stays on Earth while twin B rides the rocket at 0.99 c for 10 years. Determine how long is passed on Earth. So the equation that we're going to have is TV equals T0 over square root of 1 minus v squared over c squared. Now, we do know that if this velocity were to cancel out, that these two things would equal. So if you were to somehow move at zero velocity, these two values would be equal. But what we're trying to solve for is we're trying to figure out how much time has been dilated. So really what we're looking for is the TV term. How much has the velocity changed? Now we do know that the velocity is 0.9999 c. As you start to get closer to the speed of light, they tend to express these things in terms of c instead of writing out 2.9999999 times 10 to the 8th, because it's better just to compare it to the c value. We do know that the original time that was on the rocket was 10 years. So now, this is the basis of a lot of science fiction. We want to see how different Earth is going to be when we finish this journey. So what we're going to do is we're going to say our time that we're looking for is going to be equal to 10 years divided by the square root of 1 minus 0.9999 c, squared divided by c squared. Well, you should see that the c's are going to cancel out, and what you're going to be left with is 0.9999 squared, 1 minus that value, and then you take the square root of it. And what you end up with is a very, very small number. 10 divided by 0.01414178121. So it's just a very, very small value. Now when you take 10 and you divide it by that number, you see that 707 years has passed on Earth. So not only is twin A going to be long gone, but twin A's children and children and children and children and children are going to be gone as well. Just think about if you took this journey, okay, and you were to get back to Earth today, how different is Earth now than it was 707 years ago? It's very, very, very different. So imagine what it would be like 707 years in the future. So that's one of the things that science fiction writers kind of tend to run with, is how different is the Earth going to be? Can people live forever? Those sorts of things. So length contraction. So the other option that we had is, instead of increasing the length of time, we could actually decrease the length between objects. This is kind of confusing because people say, well, wait a second, how do you decrease the length between objects? It turns out as you get faster and faster, the objects get somewhat compressed in terms of space. So you can actually take objects that are smaller and or that are larger than an object you want to fit it in. You can fit them in if they're moving close to the speed of light. So there is experimental evidence for this as well, and one of those is that cosmic rays, which are from the sun, strike the atmosphere and produce what's called a muon. Now, these muons have very, very, very short lifespans, 2.2 microseconds. So whenever it hits here, it makes a muon. 2.2 microseconds later, that muon is gone. Okay, but for some reason, we still have muons that strike the surface of the Earth. Now, they shouldn't, because the distance that a muon traveling at the speed of light can actually travel in 2.2 microseconds is not sufficient for it to be able to hit the surface of the Earth. So the only explanation that we can really come up with that matches the theory of special relativity is that the actual length between the surface of the Earth and the atmosphere is contracted as a result of the cosmic rays moving so close to the speed of light, and the muons moving so close to the speed of light. So we have experimental evidence that both length can contract, and we also have experimental evidence that time can dilate. The equation for the length contraction is this. You have this LV term, which is very similar to our TV term. You have an LO term, and then instead of dividing by that gamma term, we actually multiply that by that gamma term. So this right here will actually reduce the length of an object the closer it gets to the speed of light, where time was actually increased the closer we got to the speed of light. Alright, in this example, we were talking about length contraction. It says a farmer wants to fit a 10-meter pole in an 8-meter long barn. You say, well, that's impossible. You can't fit something longer into something shorter, unless, of course, you account for relativity. So what we're trying to figure out is how fast he has to go. The equation we have is LV is equal to LO square root of 1 minus V squared over C squared. Now, you have to figure out what LV and LO are, but really it shouldn't be that hard. You should realize that the original length is 10, and that the other value is got to be 8, the length at a certain velocity. Now, this is actually really important because you should recognize that, hey, if I were to plug 10 here and 8 here, well, to get 8 to equal 10, I'd have to multiply by a number bigger than 1, which this cannot be, because you're taking 1 minus something and then taking a square root. So that's pretty easy once you look at it that way, that in order to get those to equal, plus if you were to somehow make a mistake here, you could always just flip them because you end up getting negative values. So we're going to say that 8 equals 10 square root of 1 minus V squared over C squared. Now, we can't really solve this all in one step like we've done in several other verb problems. So what we really want to do here is we want to go ahead and say divide both sides by 10. So when we do that, we get 0.8 equals the square root of 1 minus V squared over C squared. Now what we want to do is we want to square both sides. When we square both sides, we get 0.64 is equal to 1 minus V squared over C squared. So now we can say, all right, I'm going to take this, I'm going to move it over to that side. I'm going to take this and I'm going to move it over to that side. So what I get is V squared over C squared is a positive value because I moved it over to the other side, is going to equal 1 minus 0.64. Well, at this time, you could say, okay, well, V squared over C squared has got to equal 0.36. Well, now you've got the squared term on both of these, so you can take the square root of both of those, and you can get V over C has to equal 0.6. Well, now once you do that, you know what the speed of light is, so you multiply both sides by C, and you get V, the velocity, is equal to 0.6 C. So if a farmer can get the pole moving at 60% of the speed of light, a 10-meter pole will fit in an 8-meter barn, although very unlikely. So now you should understand the difference between normal relative velocity addition and then light relative velocity addition. You can't just add light rays together and get a new velocity. You should also understand that relativity can change the time or the length. Now, I'm not saying that has an effect like in science fiction where you can, you could shorten the distance by a whole lot, or you can live forever if you're going close to the speed of light. There is really no evidence to support that effect, the effect of high speeds on actual life. But time as we know it can be. So you should also understand that there is experimental evidence supporting the theory of special relativity.